Hi, I'm Shen Qingchao. I'm a master student from Tianjin University. I'm excited to present our recent work on the deep learning compiler bug study. This work is a joint effort of several universities. Nowadays, deep learning have emerged to solve problems in various domains, such as autonomous driving, face recognition, and aircraft collision avoidance system. Various DL frameworks such as TensorFlow and PyTorch are developed to facilitate the imitation of DL models. Depending on the use case, this model will be deployed on a range of hardware platforms. As the number of frameworks and hardware increases, there is a scalability problem, because frameworks must be manually integrated with each hardware-specific kernel library. To solve this problem, DL compilers was proposed. DL compiler takes DL model programmed on a DL framework as input and generates hardware-optimized code as output. It acts as a universal bridge between the numerous frameworks and hardware platforms. This is the architecture of deep learning compilers. Specifically, in the model loading stage, the DL compiler loads a DL model programmed on a DL framework and transforms it into high-level IR. In the high-level IR transformation stage, hardware-independent optimizations are conducted on high-level IR to reduce redundancy and improve efficiency. In the low-level IR transformation stage, high-level IR is converted to low-level IR, which is sufficiently fine-grained to capture hardware characteristics. The transformation also involves hardware-specific optimizations on the low-level IR. Finally, the optimized low-level IR is compiled to generate code deployed on the specific hardware. Like other software systems, DL compilers are subject to bugs. Bugs in DL compilers can be devastating when the incorrectly generated code are deployed for mission-critical DL applications. Meanwhile, DL compiler bugs complicate the fault diagnosis of anonymous behavior in DL applications. Besides, DL compiler may not share the same characteristics as traditional compiler. On one hand, the DL models processed by DL compilers do not have explicit logic structure. On the other hand, DL compilers have their own multi-level IR and a large number of DL-specific optimizations. Existing test generation and bug localization methods for traditional compilers may not work for DL compilers. Therefore, it's very important to study bugs in DL compilers. In this study, we selected the three most popular DL compilers as subject, including TUM from Apache, Blue from Facebook, and ngraph from Intel. Since our study aims to investigate the characteristics of DL compiler bugs, we collected closed and merged pull requests that are responsible to fix bugs from their GitHub repository. Then, we identified bug-fixing pull requests whose title or tags contain at least one bug-related keywords, such as fix, bug, error. For these bug-fixing pull requests, two of our authors independently label it, manually identify the root causes of bug, the symptoms that bug exhibits, the stage it occurs. After conducting two training sessions, the coin-callback efficiency of iterate agreement between them was more than 95%. During the labeling process, we remove the pull request which is not related to bug and split the pull request containing multiple bugs. In total, we collected more than 1,000 bug-fixed pull requests and identified 603 bugs. In this study, we designed 5 research questions to investigate the root causes of bug, the symptoms that bug exhibit, the relationships between symptoms and root causes, the stage bug occurs, and the commonalities of the bug in the 3 different DL compilers. After finishing the classification, labeling, and analysis, we got the answer to the 5 research questions. The figure shows the number of DL compiler bugs by their root causes. Firstly, we find that time problem is the most common root causes. The table on the right further shows the time problem bugs distribution by subcategories. We find that tensor type problem is the most common subcategories. Meanwhile, we can find that tensor shape problem is the third most common root causes. A large proportion of bugs are related to the type and shape of tensors in deep learning computations. Therefore, new criteria can be defined to measure the test coverage of tensor type and tensor shape. This figure shows the distribution of DL compiler bugs by symptom categories. It shows that crash is the most common symptoms in all the three DL compilers. Meanwhile, nearly 11% of crash bugs have ambiguous or wrong crash messages. Therefore, it's necessary for developers to provide precise and informative error messages, which could facilitate an understanding of crash bugs and their design automated localization methods. Wrong code is the symptoms that a DL compiler produces a wrong result or middle result without crash. It's the second most common symptoms of DL compilers. Generating high-quality test oracle for wrong code bugs is challenging. To facilitate their detection, one potential direction is to transform some wrong code bugs to crash bugs by adding more checks, such as assertion in DL compilers. This table shows the number of DL compiler bugs caused by each root causes which its symptoms. From the table, we can find that code logic bugs are common in DL compilers. They can induce all kinds of bugging symptoms except build failure. Among the incorrect code logic bugs, more bugs caused by incorrect optimization code logic than incorrect no optimization code logic. Therefore, design tests that can trigger virus optimizations and their combination is a promising research direction. This figure presents the bug distribution among the three DL compilation stages. Front-end bugs in traditional compiler are rare, but the number of DL compiler bugs in the model loading stage is not trivial due to the diverse input representation from various DL frameworks. It suggests that bugs in model loading stage also deserve attention. Meanwhile, it's necessary to consider various DL frameworks when constructing tests. To measure the commonality across DL compilers, we calculated the spearmine correlation between each pair of DL compilers in terms of root causes distribution and symptom distribution. We find that the three DL compilers share significant commonality in the root causes and symptoms of bugs. Therefore, it's feasible to develop solutions that can generalize to different DL compilers for the detection, localization, and fixing of DL compiler bugs. To demonstrate the usefulness of our finding, we designed a preliminary proof of concept application TM-FAS. TM-FAS uses two findings. One is bug arising from tensor type and tensor shape are common. Another is high-level IR transformation is the most error-prone DL compiler stage. It aims to generate unit tests in TM based on existing tests. First, from the existing unit tests for the high-level IR transform stage, TM-FAS learns the relationship of those API to construct a directed graph. Secondly, it randomly selects a subgraph and then mutates the tensor type, tensor shape, node name, and the primitive value of tensor elements to construct a mutated subgraph as a new unit test. We apply TM-FAS to TM via differential testing, and the test oracle is whether a test produces consistency result between the two TM versions. Finally, we find 8 bugs in total shown in the table. We have released our design and tools on GitHub. More details about our level designs and TM-FAS can be found on our homepage. In the presentation, we conducted the first comprehensive study to understand DL compiler bugs. We manually studied 603 bugs from 3 popular and diverse DL compilers, identified 12 root causes and 6 bug symptoms, and obtained 12 major findings. Based on these findings, we provide a series of guidelines for DL compiler bug detection and debugging in the future. In addition, we made the first attempt to design simple but effective TM testing tools, TM-FAS, and find 8 TM bugs which can demonstrate the practical potential of our finding. Thanks for your listening.